This is my first video lesson for Unit 8, the gas laws. In this lesson, we'll be describing the behaviors of gases. Go to page 2 in the class packet. You can download the class packet on my website. Motivation, this is review. Complete the properties of a gas. The shape of a gas is indefinite. It takes the shape of a container. The volume of the gas is also indefinite. It's based off the container. The particle distances in the gas is var. The particle arrangement in the gas is random. Learning target. At the end of the lesson, I'll be able to define pressure and explain the kinetic molecular theory, KMT. Homework number 1 will be a Junipod based off this lesson. What is pressure? Pressure is defined as force over an area. In terms of a gas, a pressure of a gas is the sum of the forces of the gas particles hitting the walls of its container. The container is the area. Here we have a particle diagram of gas particles. The gas particles are always moving. They will exert a force. The size of the arrow represents the force. So when the gas particles hit the container, that's when the pressure is exerted. Here's a GIF of the gas particles hitting the container, exerting pressure. What factors can affect the pressure of a gas? Think about what factors that can affect how often the particles will hit the walls of the container. So the 4 factors are temperature, the volume of the container, the pressure outside the container, and the amount of gas inside the container. Let's look over some scenarios of the factors that affect pressure. Here we have some gas particles in a container. If we add heat, the gas particles will move faster, therefore exert a greater force on the container. So the speed of the particles increases, and the pressure will increase because the particles are exerting a greater force on the container. In the second scenario, we decrease the amount of gas particles. So notice that the amount of gas particles decrease. The speed of the particle is constant because the temperature is constant. Temperature is the average kinetic energy. Since we have less particles, there's less particles hitting the container. Since there's less particles hitting the container, the pressure would decrease. In the third scenario, we increase the amount of gas particles. So the speed of the particles will be constant because the temperature is constant. The pressure will increase because we have more gas particles hitting the container. In the next scenario, we will be increasing the temperature by adding heat. By adding heat, the particles will move faster. Therefore, the speed of the particles will increase. The pressure will also increase because the particles will be hitting the walls more often at a greater force. In the next scenario, we're going to decrease the volume of the container. Notice we have the same number of gas particles, so the speed of the particles will be constant. The pressure will increase because the particles will be hitting the container more often in a smaller space. Here's a GIF to demonstrate that. If we increase the volume, we'll get the opposite effect. The speed will remain constant and the pressure will decrease. We will be discussing real and ideal gases. Real and ideal are opposites of each other. Real is something that can be found in reality. Ideal is imaginary. The reason why we'll be studying ideal gases versus real gases is because real gases are harder to study. Their properties are more difficult to determine. Ideal gases are easier to study because we'll be imagining perfect conditions. We'll be simplifying the model in order to explain gas behavior. The kinetic molecular theory explains the behavior of ideal gas. As the temperature increases, the speed of the particles will also increase, the energy will increase. Kinetic energy is equal to 1/2 mass times velocity squared, which is also equal to 3/2 Boltzmann constant times temperature. This is the Boltzmann constant. Now we're going to go over properties of ideal gas versus a real gas. There are 2 assumptions made about an ideal gas. The first assumption is that gas molecules themselves have no volume. The second assumption is that gas molecules have no intramolecular forces. Because of these 2 assumptions, the properties of an ideal gas is different from a real gas. In an ideal gas, the gas molecules are continuously moving in a random and straight line motion. When gas particles collide with each other or with walls of the container, there is no energy loss in ideal gas. There is a transfer of energy when the particles collide, but there is no loss in energy. The total energy of a system will remain the same. For the volume of ideal gas, the volume of the gas particles is insignificant, negligible, when compared to the volume of the container. The gas particles are separated far apart. As a result, the gas particles themselves have no volume, but the gas still has volume. It will be based off the container. There is no attraction or intramolecular forces that exist between the molecules, so these are the properties of an ideal gas. For a real gas, they will have properties opposite of those in ideal gas. Real gases do not move in straight lines due to intramolecular forces. There are energy transfers between gas molecules and the container, but it is lost to the surrounding environment. Gas particles do have volume, they do take up some space. Attractions or intramolecular forces do exist between the molecules. Just to review, the reason why ideal gases differ from real gases is because of the two assumptions. The gas particles have no volume and they have no intramolecular forces. While real gases, the gas particles do have volume and they do have intramolecular forces. I highlighted all the key points of the properties of an ideal gas and a real gas. The ones I highlighted are typically asked on the Regents. So here will be a diagram showing the ideal gas and a real gas on how they move. Learning check number 1. According to the kinetic molecular theory, which statement describes one characteristic of an ideal gas system? Pause the video and resume as completed. So let's look at each choice. The distance between gas molecules is smaller than the diameter of one gas molecule. So the gas molecules are far apart, so choice 1 is wrong. The attractive force between two gas molecules is strong. In ideal gas, there is no attractive force, so choice 2 is wrong. The energy of the system decreases as the gas molecules collide. There is no loss of energy when the gas molecules collide. They're not losing any energy to the container, so choice 3 is wrong. The straight line motion of a gas molecule is constant and random, so the answer is choice 4. Learning check number 2. Which statement describes particles of an ideal gas based on the kinetic molecular theory? Pause the video and resume as completed. Gas particles are separated by distances smaller than the size of the gas particles. So the first one's wrong because gas particles are far apart. And number 2, the gas particles do not transfer energy to each other when they collide. They do transfer energy, so choice 2 is wrong. Gas particles have no attractive forces between them, so choice 3 is correct for an ideal gas. Gas particles move in predictable and circular motion. That's wrong. Gases move in straight line for ideal gases. Learning check number 3. According to the kinetic molecular theory, which statement describes the particle of an ideal gas? Pause the video and resume as completed. So let's check each statement. The gas particles are arranged in a regular pattern. This is wrong because gas particles are arranged in a random manner. The forces of attraction between gas particles is strong. In ideal gas, the gas particles have no intramolecular forces, so this is wrong. The gas particles are hard spheres in a continuous circular motion. In ideal gas, gas particles move in a straight line, so 3 is wrong. The answer is choice 4. The collisions of the gas particles may result in a transfer of energy. Check of understanding number 1. What causes non-ideal behaviors in real gases? The particles of real gases have volume and intramolecular forces. Check of understanding number 2. Under what conditions might a real gas behave like an ideal gas, and why? Under high temperature and low pressure, you have to memorize this for the Regents exam. So why high temperature and low pressure might a real gas behave like an ideal gas? Under high temperature, it means there's more energy for the gas particles to overcome the intramolecular forces. Under low pressure, it means there's a larger volume. Therefore, there's less intramolecular forces because there's more space. So the reason why high temperature and low pressure causes real gases to behave ideally because you lessen the intramolecular forces. Learning check number 4. Under which conditions of temperature and pressure does a real gas behave most like an ideal gas? Pause the video and resume to complete it. The answer is choice 3, high temperature and low pressure. Learning check number 5. A sample of chlorine gas is at 300 Kelvin and 1 atmosphere. At which temperature and pressure would the sample behave more like an ideal gas? Pause the video and resume to complete it. So expecting a higher temperature and a lower pressure, so the answer is choice 4. Check of understanding number 3, state a substance that will behave the most as an ideal gas. So you're looking for a gas particle that's very small and does not exert a lot of intermolecular forces. An example of this would be helium or hydrogen. So this concludes the video lesson. Remember to do the Junipod homework.